SwayamPrabha. Digital India. Educated India.
Hello and welcome to the course on manufacturing technology theory and practice. We are now going to demonstrate the working principle of grinding machine, and overall I am going to give you an idea about the grinding. Although you have listened to some of the grinding theories in the lecture sessions, but nevertheless here is the grinding machine. So, particularly this grinding machine is a tool grinder, we call it, because in this lab we need to grind the tools. However, we can also make the surface grinding to grind the surface, as well as we can make the grinding for the drill, all right, which is very important for our lab. So, you can see this is the spindle of the grinding machine, and this spindle and the mandrel of the spindle, the grinding wheel, cup type grinding wheel is mounted, and here we will have the tool that is to be mounted. See, today first we will show you the turning grinding of the side rake angle. This is the turning tool, as you can see. This is the rake face of the tool, and the inclination of the rake face, that is defined by the side rake angle, that we will show it to you. That means, this is the angle between the rake face and a line, which is this line, which is perpendicular to the cutting velocity vector. So, this angle between this scale edge and this surface, which is the rake surface, this angle will be the side rake angle. You can see that there is an angle, you can focus it here, and you can see that there is a certain angle between the edge of the scale and the surface of the tool, which is the rake face, all right, which is the side rake angle. So, this side rake angle will define the inclination of this rake face, and as I already told you in the lectures of the course, that the side rake angle is one of the important angles, because the side rake angle also defines the cutting power and the cutting force, meaning that if the side rake angle is changed, the cutting forces will be changed and ultimately the power will be changed. So, those details have been given in the lectures, that you can see those lecture sessions. So, we will show you how this angle can be ground. Now, why we need to grind the angle? Now, the tool, as you know, that when it works, the surfaces wear out. Now, this is the rake face, where the wearing takes place in the form of a crater wear, and this is the flank surface, which wears out because of the flank wear, and the flank wear is due to the rubbing of the flank face with the already machined surface, and the crater wear that takes place on the rake face is because of the because of the chip sliding along the rake face. So, there will be a crater formed, which will be some distance away from the tool tip. So, those details are given in the lectures. So, now coming to the grinding, apart from this kind of a grinding wheel, you can see that another grinding wheel is it can be like this, okay, or a grinding wheel for the profile grinder module cutter. For example, we grind it with this. You can see that this is a thin grinding wheel. This is made for the profile, for grinding the profile. So, it will be inclined to this one profile, and then it will be inclined to this. So, it will be another profile, and so on. Another grinding wheel is the cup type grinding wheel. These are all mounted on the mandrel of the shaft of the spindle, the grinding wheel, which rotates, and the grinding wheel rotates, which actually is the cutting speed. Okay. Now, another grinding wheel, you can see this kind of a grinding wheel, These are also used for grinding the tool angles, different kind of tool angles and so on. Now, regarding the grinding wheel, I will just remind you that there are 5 parameters which actually define the working of the grinding wheel. Now, if you see the grinding wheel, the first parameter that you can see, which is the type of the abrasive material. So, basically there are 3 types of abrasive materials which are used. I am repeating once again, these are details are you can see in the lecture material. So, either it can be Al2O3, aluminum oxide, silicon carbide or the diamond, all right. So, aluminum oxide, silicon carbide or the diamond, they are used depending on what kind of material, workpiece material you are grinding. For example, for the grinding of the steel, okay, or the hard material, high strength material, then the aluminum oxide Al2O3 abrasive grains should be used. For silicon carbide, when the silicon carbides used as the grains of the grinding wheel, there the materials like aluminum, materials like copper or materials like brittle material like cast iron or high hard materials overall, they are that is the workpiece material. They are used to grind with a grinding wheel with silicon carbide grains. Now, the silicon carbide grains, they are of course more expensive than the aluminum oxide grains, and the diamond grains are exclusively used for very hard materials like glass or the hard materials like Yukon and so on, which are used these days for the tool materials. So, for grinding those kind of tools, sharpening those kind of tools, you have to use the diamond grinder. Now, the diamond grinders are very expensive because the grains will be the diamond grains, and they are used for exclusively for very hard and brittle materials like glass is can be ground only with the use of the by using the diamond grinding wheels. So, that is the first performance, that is what kind of abrasive materials that you can use in a grinding wheel. The second parameter on which the performance of a grinding wheel depends, it is the size of the grain. Either you use a coarse size, that is the bigger size grains, or you can use the medium size grain, or you can use the very fine grains, okay, fine grains and very fine grains. So, these are the 4 basic grades which are available, that is coarse, that is medium, that is fine and the very fine grains, all right. Now, the grinding wheel grains, diameter of the grinding wheel grains, that depends on this sieve number. So, the sieve number defines the size of the grinding wheel grain. That sieve number is given by Sn, let us say. So, more the Sn value, less will be the diameter. Okay. So, there is a formula according to that you can find out that what will be the diameter of the grinding wheel. So, basically this is inversely proportional to the sieve number, and the sieve number, as I said in my lecture class, that this is defined by 1 inch by 1 inch sieve and how many openings are there. By 1 inch and 1 inch sieve, if the openings are let us say 600, so in that case the abrasive grains which will pass through that kind of a sieve will have an Sn number of 600, and the diameter will be proportional to that, that is 1 by Sn, that is 1 by 600. So, you can understand that those diameters will be very, very fine. So, those are the very fine grains. Now, where those kind of grains are used? As I said earlier in the lecture material also, that very big grains or the coarse grains, they will remove basically more material because the grains are very big, all right. And since they are removing more material, then the surface finish will not be very good. So, surface finish will be good if the grain size is small, when the surface, when the material removal rate is less material is removed. Now, if the number of grains or the size of the grain is very big, in that case the number of grains will be limited, there will be smaller number, because the grain size within a given diameter of the grinding wheel will be bigger size. So, the number will be less of course. Now, the third parameter on which the performance of the grinding wheel depends, it is the grade, and the grade defines the strength of the bonding material, how well the grains are bound with each other. So, you understand that when the grinding wheel will be working, each grain inside this grinding wheel, they are bonded, they are bound with each other, and that is done by a resin, some kind of a resin. There are different kind of resins used for this purpose, and how strongly those bonds are, and how strongly the grains are bound to each other, depending on that the strength of the grinding wheel will be defined. Meaning that if the bonds are very strong, then the grinding wheel grains will be very strongly, very rigidly bound with each other, and it will not be easily dislodged. So, what happens then? There is a problem with that in case the grinding wheel is hard, in the sense that grinding wheel bond is very strong, and you are using, suppose, very hard material for grinding, workpiece material for grinding. Now, since the workpiece material is very high, then those grains which will be on the surface of the workpiece of the grinding wheel, they will be worn out very quickly, because the material of the workpiece is very hard. Now if the wheel is very strong, then those worn out grains will not be easily dislodged, and they will stay on the periphery, on the surface of the grinding wheel. What is the problem with that? That they will stay at the surface, and they will not allow the other sharp grains to be revealed, which are below them. Okay. So, therefore, those worn out grains, they will start removing material, and as you understand that since they are not sharp, so then they will rub more, they will consume more power, and they will consume more force without removing much of the material. So, that is a very negative factor for the grinding process, and in that case it is said that the grinding wheel is glazed, that is called the glazing of the grinding wheel, because those worn out grains which will be on the surface of the grinding wheel, which are not coming out, they will look like a glazed surface. Okay. They will make the grinding wheel look like a glazed surface. So, that is not good. Then those glazed that worn out grains, or the glazed layer, has to be removed forcefully, and that removal is done by a diamond pencil, which process by which this is done is called the wheel dressing. You might be knowing that. So, wheel dressing is nothing but removing those worn out grains from the surface of the grinding wheel, when particularly the grinding wheel is very hard, and those worn out grains do not dislodge from the grinding surface very easily. Now, the next parameter on which the grinding wheel performance depends is the structure of the grinding wheel. Now, you can see that the grinding wheel, by looking at the grinding wheel, you can say that the grinding wheel is very densely packed, or it is very loosely packed, in the sense that the voids between the grains will be smaller. Voids are those spaces between the grains, like in the case of milling cutter, for example. In milling cutter, between the teeth there is a space, and that space is provided to accommodate the chips. Now, similarly, in case of grinding wheel also, in between the grinding wheel grains there is a space, and that space is actually given for accommodating the small chips, okay, the chips which are very small anyway for the grinding process. Now, if those voids are very small and the grinding wheel chips are small anyway, so those grinding chips will be staying in those voids and won't be able to come out. Then what will happen is that all along the surface of the grinding wheel, those chips will be nested, and instead of the grains cutting the workpiece, removing the workpiece material, the nested or clogged chips will be rubbing, and that will also consume more power. It will rub, and the force will be taken more without removing much of the material. So, that is also a negative factor, like in case of the wheel glazing, but in this case it is called the wheel loading, that the wheel has been loaded. Okay. Again, those chips which cannot come out because the voids are small, they have to be forcefully taken out, and again the wheel dressing is required, like in case of the glazed wheel. So, then there are 17 structures of all the grinding wheels, and that is an international standard. All over the world these 17 structures are used from 0 to 16. 0 is dense, to open is 16. So, altogether there are 17 structures. 0, 1, 2, 3, 4, these are very densely packed grinding wheels, and starting from 8, 9, 10, 11, 12 and so on up to 16, they are loosely packed, meaning that the voids are very big and the bigger chips can be accommodated there. So, that will be for rough operation, for example, where the chips are bigger in size, and to accommodate those chips in the void so that they could come out, those voids have to be bigger. Now, finally, another parameter on which the performance will depend is the bonding material. So, there are different kind of bonding materials, as I said. Some of the bonding materials are vitrified bond, resinoid, shellac, rubber, metal bonds and so on. Silicate is another bond, which is very interesting bonds, which are used for so to say cool operation, meaning that when you are using the silicate, then that bond will allow you to make the grinding wheel so called softer, in the sense the grains will be dislodged easily. Okay. That means, if you have a very hard material and if you are using the silicate bond in the grinding wheel, then the worn out grains will be easily dislodged, and those grinding wheels are used for grinding the small space in the tool, because only the tool tip has to be ground, for example, tool tip has to be resharpened. Okay. In that case, you do not want the very high temperature to be produced, so that the vicinity of the tip is not thermally deformed. All right. In that case, you have to be very sure that temperature rise is not much, and since in grinding the grinding velocity is very high, which is 10 to 80 meter per second, and you can understand that 10 to 80 meter per second is a very high speed, and at that speed the temperature occurring will be very high. So, you can see, even you will see here that when the grinding process will be on, there will be those chips which are so small, and they will be flying away in terms of the sparks. You can see the sparks, they are actually burning. Temperature may go up to 1500 degrees centigrade. So, at that temperature, those small chips which are of the steel, which are of the tool material, they can actually burn. So, therefore, we do not want the temperature to rise very high, and temperature may not rise very high when the cutting is done by the sharp edges, okay, and not by the dull edges, because as I said, the dull edges will rub more, it will produce more temperature. So, the silicate is one bond which actually is used for the cool operation, so that during the grinding process the temperature does not rise very high. So, these are the 5 parameters which are very important for the grinding wheel. For any grinding wheel that you take, be it a tool grinder, be it a surface grinder, or be it a drill grinder, okay, the performance of the grinding wheel overall should be controlled by controlling these 5 parameters together. Then only your result or the grinding process will be effective, grinding process will be accurate and so on. So, here in this we are going to show you, as I said, the grinding of the tool. Now, during the once again I will repeat that during the process, during the cutting process, these surfaces will be worn out, particularly the rake and the flank surface, and the angles that you provide initially for the sharp tool, those angles will be distorted. Now, as those angles are distorting, in that case the force requirement, the power requirement will be changed, and therefore, those angles have to be restored. All right. So, for restoring those angles to the previous value that you have selected, you have to regrind the tool. And right now, we will show you how a tool can be reground, so that the worn out surfaces are established, are compensated for, and the initial angle that you have selected can be established. So, Mr. Aman Singh will show you how this tool can be reground, or particularly this side rake angle, as we said, and I have shown to you the side rake angle here. So, this angle particularly will be restored and reground, so that it could be the angle obtained will be as per the initial value that we have selected. The grinding process is required. Let us say worn out tool, the one that I have shown it to you, and this is clamped in the vise, which is in this case is the tool post, all right, and the grinding wheel mounted already there in the mandrel. Now, initially you make the 0 point, that is you touch the grinding wheel with the surface that you are going to grind, and the speed can be selected by the selector. It is there in that machine, by which you can select different kind of speeds that is will be required here. So, now you can see that how what is the speed of the grinding wheel. It is rotating at a very high speed, and at that high speed the grinding process will be performed. So, that is in touch with the rake face of the tool, okay, and the side rake angle will be established. You can see this spark. That spark, as I said, is nothing but the small chips being burned at the temperature of 1005 up to 1500 degrees centigrade. That tool material is the high speed steel material. Okay. So, he is giving the feed manually, and it has to be given very slowly. The feed speed of the feed should be very small. It will be about 0.2, 0.6 meter per second, not more than that. See, in this case the setting of the tool is very important, that how you are going to set the tool, so that the grinding process can be performed to get that rake angle, particular rake angle. If you incline the tool, for example, the rake angle which will be ground, it will be distorted. It will not be the same rake angle as you have initially selected. And that angle that you require, this angle set, as I was telling, the tool has to be set very carefully. This angle is selected by this dial. Okay. This dial is graduated and it can be rotated, so that according to that angle which you require, that angle can be given here. Okay. So, it is not simply given the mounting the tool, but mounting the tool at a certain angle at which the side rake angle that you want to regrind, that can be established. So, this is important. As I said, that angle cannot be arbitrary angle. And now, if you see, if you concentrate, this looks little burnt, because at a high temperature there is burning tendency, and that is why this and this is hot actually. I am holding it, but it is hot, and this color came because of the burning of the surface to a certain extent. However, this does not affect the it does not make that thermal distortion of the vicinity of the tool. However, if at a very high temperature it happens, then it may be distorted, meaning that other angles which are there, they may be distorted. So, that has to be protected. Okay. Therefore, we need to have those kind of grains which will be, or grade which will be softer, that can allow the grains to dislodge. So, that sharp grains can always cut the remove the material, and temperature occurring could be less. I gave you an example of silicate as a bond. That is an example of making a softer wheel. We are going to demonstrate another grinding process, which is the grinding of the drill. Now, if you can see this drill. So, we have to grind these two faces, all right, and these two faces together, they make and in between they make an angle of 118 degree, that you must be knowing, because this is the cutting angle of a drill, which is a standard value. So, between these two faces, this angle is the cutting angle and we have to face this. So, therefore, here if you see that this is an attachment and this attachment helps in grinding these two faces of the drill. Now, first of all we have to set at an angle of 118 degree. So, this is the measurement for the measuring of angles that I have shown it to you. Now, here we have set it, let us see how much it will show. So, if you put this here, okay, between this, here it is set, if you can see this, yes. So, here it is showing 90 plus 18, so it is 118 degree, okay. Through this we can see this. Now, at this angle we have to set this attachment, and here there is a scale, the scale is graduated. We have set it at an angle of 118 degree, meaning that if we now move this in this way, all right. So, in that case the face will be in touch with the grinding wheel, because it is set at 90 plus 18, 118 degree, sorry, 90 plus 28. So, it is 118 degree, and in that case it will be just ground like this. Now, for the other face we have to just rotate that the drill in this attachment itself, and the other face can be ground. So, now we will show you how we will switch on the machine and we will show you how these two faces are ground. Now, you can see that the face of the drill is getting in contact with the grinding wheel, and the face will be ground. This attachment, as it is as I said that this is set at an angle of 118 degree. So, that is the angle of the cutting, that is the cutting angle of the drill, and now that face has been ground. So, next for the another face we have to rotate the tool. As you can see this, it is being rotated and the other face is ready for being ground, and that face is now in touch with the grinding wheel, and the other face is now being ground. You can see this. So, this grinding wheel is a special grinding wheel, because you can see that the face of that grinding wheel is actually grinding the drill. All right. It is not the outer surface, but it is the face of the grinding wheel. So, this is a cup type grinding wheel which is used for grinding the drill. Well, to continue with the grinding process, now in the same machine you can see that the grinding wheel has been changed. Earlier, if it was a cup type grinding wheel which was used for grinding the tool, okay, side rake of the tool, and then the face of the drill, but here we have changed the wheel to a wheel which is capable of doing the surface grinding. So, surface grinding, as you know, that this is making a flat surface. So, here is the wheel which is used for the surface grinding. This is the workpiece, and this workpiece will be ground. All right, surface grinding of this surface will be made, and this is a ferromagnetic material, and this workpiece is mounted on a plate which has a magnet. All right. So, this can be demagnetized or magnetized depending on the handle. There is a handle. So, this handle will make this magnetic or non-magnetic. When it is when the clamping has to be done, this workpiece will be clamped very rigidly. You can see that it is very rigid because it is a very strong magnet, and then afterwards the entire thing is mounted on the bed of this machine, grinding machine. So, mind these clamps. Okay. This is the clamp, and here depending on this thickness, the clamp height can be changed because it has the rack cut on this as well as on the other face which is mating with this. This clamp we have shown earlier when we were showing you the tools and the fixtures, all right. So, both of them are here. Here it is on the other side there is another clamp and the mechanism is the same. This is the clamp, and you can see that this entire setup, that is the magnetic clamp, this is mounted on the on this bed, okay, with these two clamps. Now, this is ready for grinding. This is the axis of the grinding wheel, this is the arbor, and on this at the end of the arbor the grinding wheel is mounted, and you can see the mounting of the grinding wheel, which is little different than the one that you have seen for the grinding of the drill or the grinding of the turning tool. So, now when this machine will be on, it will be demonstrated to you, and then you will see that you understand that this will rotate, okay, and the table reciprocates, all right. Now, the reciprocation will be done, will be shown to you manually, so that it could be visible in a better way for you, but otherwise you know that this is done hydraulically. There is a end switch, and this end switch makes that reciprocation possible. So, right now it will be shown to you mechanically, I mean manually, so that it can be more understood for you. Okay. So, Mr. Srinivasulu will demonstrate how this surface grinding process can be accomplished. Yeah. So, the machine is on, and you can see the grinding wheel is rotating at a very high speed, and I told you that the speed of the grinding wheel is about 10 to 80 meter per second. So, it rotates at a very high speed. The feed is given, which is by rotating the handle, as you can see that, and the surface is being ground. So, this is the reciprocation that I was telling you, that the table along with the workpiece is reciprocated, and the entire surface is getting ground. So, the entire width, to get the entire width ground, you have to have the feed in the y direction. That means, in the feed direction, that is in the longitudinal direction, you are having the reciprocation, and in the cross feed, that is perpendicular to the longitudinal feed, you have to have the feed to get the entire width covered. Okay. So, pass by pass, the entire surface will be ground. In each pass, one segment of the width is being ground, and when the cross feed is given, finally the entire width and the entire surface will be ground. That is the idea. So, you can see that it is rigidly mounted on the magnetic plate. This is how the plates or the workpieces are mounted during the surface grinding. So, I would like to demonstrate another mechanism which you can see here. This is the gearbox in the cutout, where you can see that how a gearbox in a car, in a vehicle, it works, and how the gears are changed. So, this is the handle. Now, this handle is in the neutral position. So, this shaft is the input shaft, okay, and this is the output shaft, meaning from here the transmission goes to the wheels, either to the wheels where the transmission is required. It may be rear wheel, it may be sometimes it may be front wheel, depending on the type of the car. So, at this moment it is in the neutral position. So, if you rotate this, you can see that the output shaft is not rotating because it is in neutral. So, this is the clutch, and this clutch is in the disengaged position. So, that if you rotate this input shaft, and you know that input shaft is rotated by the engine, and that engine is the internal combustion engine. I am talking about the vehicle. It may be a car, it may be bus, it may be truck, Okay. So, that internal combustion engine that supplies the power to the input shaft, and this shaft is connected to the output shaft of the internal combustion engine. So, then when you are changing the gear, all right. So, at this moment, as I said, this is in the neutral position. So, this is disengaged with the motor, output shaft is disengaged with the motor. Now, here what happens is that there is gear train. As you can see that this gear is meshing with another gear, then the transmission goes to the intermediate shaft, and from here this gear goes into this. These are the spar gears, these are the helical gears. Well, and you can see that this is the bigger one, this is the smaller one, this is the bigger one, this is the smaller one. So, the depending on which gear is meshing with which one, you will get the transmission ratio. For example, if your input shaft is rotating and you want a higher rotation to the output shaft, for example, in case of higher gears, that is 4th gear or 5th gear, you want the output shaft to rotate at a faster rate than the input shaft. In that case, what happens? You have to actually transmit that with a higher transmission ratio. So, from a bigger gear, it has to go to the smaller gear at the output, and vice versa when you need to have the smaller RPM, for example, in the first gear or in the second gear, all right. So, in the first gear and second gear, what happens is that the input shaft has a smaller gear. By smaller gear, I mean to say the number of teeth will be less, and similarly the diameter will be less, accordingly the diameter will be less. So, if a gear with a less number of teeth transmits power to the gear with the larger number of teeth, in that case the RPM of the output shaft will be less than the RPM of the input shaft, because the transmission ratio is accordingly made. So, this is N1 by N2, so which is actually less. Now, here also another thing, that in the first and second gear you have to have a larger torque. So, as the RPM is less, so the torque will be higher, and as the gears are changed, meaning that as you are transmitting from a bigger gear to the lower gear, the RPM will be more and the torque will be less, torque transmitted will be less. So, at the lower gear, when the car is just starting, you have to overcome the friction between the tire and the road, okay, and the car is very heavy. So, that friction force is very high. So, you have to overcome that, and because of that you need to have a very high torque, but your RPM or the speed should be low. But as you go, as the car has started going, it already has the inertia. So, you do not need the higher torque than the first and the second gear, and you will have the less torque carrying capacity to the output shaft with respect to the input shaft, and your RPM has to be more, because at 4th gear and 5th gear the car speed is higher. So, now if you change the gear, so some gear, for example, you have changed here. So, if you see that now, if you rotate this, this will be rotated, and as you can see that this is transmission is going from the bigger gear to the lower gear. Bigger gear means the more number of teeth to the less number of teeth. So, therefore, the speed here is high, as you can see the speed is higher, all right, of the output shaft, and so on. So, there are first gear, second gear, third gear, up to 5th gear, and there is a back gear as well. So, Mr. Aman is going to demonstrate how those gears are changed. You can see that lever, the lever has different positions. So, you take it in different positions. You remember that in car it is 1, 2, 3, 4, 5, 6, 5 and the back gear. So, this is the first gear. So, first gear means lot of torque is transmitted and the RPM is not very high. So, in that case the smaller gear transmits the power to the bigger gear. You can see that now it is faster. So, this is second gear, all right. Now, the position is changed and this is the third gear, all right. So, in third gear the torque is relatively less and the RPM will be more. In fourth gear torque is even less, but the RPM is higher, as I was telling. Okay. And here if you see that this is the back gear, and in the back gear this is input shaft is rotated in this way, and you see this output shaft is rotating is in this way. So, this is the back gear. So, this way the gear is changed with the help of this, and then you can actually put it back to the neutral position, and neutral position means with the rotation of that you can see that this is not rotating. So, this is how in a compact way the gear drive or the transmission ratio is made in the gearbox of an automobile. This is also a gearbox, but here additionally what we are showing is that you remember that when it is kick starting, let us say in a scooter, okay, or in a two-wheeler which is lighter than the vehicles. So, here you actually start, and when you are starting, there are two ways of starting that. These days of course, there are electronic starter, and along with that there is a starter which is you are kicking. So, for example, if you are kicking, you can see that this is rotating at a faster rate, and then it actually starts. I mean, this vehicle is getting started. Vehicle means here this is particularly for three-wheeler, scooter, motorcycle, such kind of gearboxes are there. This is, you can see, the smaller than the previous one which was used for vehicles. So, here this is the kick start. Okay. You can see that the ratchet mechanism which makes that sound, all right, and when you are kicking you can see that this is moving. So, this rotation is being imitated by the this kicking mechanism, all right, and after that with inertia it can actually get started, as it is done in case of motorcycle and scooter. Here you can see the differential mechanism of an automobile, and you know what is differential mechanism. This is for the rear wheels, where the transmission is given from the internal combustion engine, particularly when a vehicle takes a turn. In that case what happens is that the velocity or the speed of the one gear which is at the end of that road, the other side of the road, is more than which is in the inner side. Okay. And this is simply because when when you are considering the speed of the outer wheel, there the radius is more, and therefore, you know that the speed is given by pi d n. Pi d is the diameter and n is the RPM. RPM being the same because this is the internal combustion engine which is used, all right, and diameter is changing. So, if the diameter is more, the speed will be more, and when it is taking a turn like this, in that case this wheel, outer wheel, will have a bigger diameter and the inner wheel will have a less diameter. So, then the speed is changing. So, now when the speed is changing and the RPM being the same, you have to have a mechanism so that these two speeds are different. That is why the mechanism is called the differential mechanism. And you can see here in this mechanism, this is the input shaft from where the power is transmitted to this is the axle of the rear wheel where the transmission goes in, and as you rotate here, from the input shaft through the spiral gear, it is connected to another spiral gear of the output shaft, okay. And this spiral gear of the output shaft, this is connected to other gears with the planetary drives. Okay. There are 4 planetary gears, and each of them has a transmission, has their own transmission ratio, and this is given different transmissions to the right wheel and the left wheel. And therefore, as a result, if it is rotating, for example, as the input shaft, you can see that both of them are rotating in a normal case. But when it is taking a turn, suppose this wheel has the less velocity, let us say 0, okay, taking a very abrupt turn. In that case, this is stopped, as you can see that this is not rotating, but still this is rotating, because the input shaft is rotating at a constant speed. There is no change in the RPM or the speed of the input. So, this is the constant one, and now in normal case, once again, when the input is given, both the wheels are rotating, but in case when it is turning, so in that case when you rotate even and this is stopped, okay, and that is still rotating, you can see this. Or if you still rotate, stop this, that will rotate. So, if it is taking a turn to the left or to the right, this is what will happen, okay. And this is done by the mechanism that I have shown it to you. This is the differential mechanism, that is why it is called the differential, because there is a difference in the speed between the two wheels, and this is done by the planetary wheels, and planetary wheels are connected to the other wheel which is on the shaft of the other wheel, all right. So, basically once again this spiral gear of the input shaft is connected to the spiral gear of the shaft of the output, and then in its turn that spiral gear with the help of the planetary gear is connected to the output to the other wheel. Again shaft is the same, but on this output shaft there are two wheels. These two wheels are independently mounted with the help of this gear drive, okay. So, that is why I am saying it is independently mounted, in the sense that when this is rotating, this may not rotate because of that mechanism. So, this is what happens and what we need when the car takes a right turn or the left turn. So, the wheel speeds have to be different, and that differential in the speed is made possible by the differential mechanism, which is used in automobiles, let us say SUVs, trucks, buses, and so on. Well, now we are going to demonstrate you the principles and the working of the computer numerically controlled machines. So, in this section, that is in this lab, we have few turning and the milling computer numerically controlled machines. So, I will like to remind you that computer numerically controlled machines, they are different from the conventional machine in the way that each axis in the computer numerically controlled machines, that is the x, y and z, each axis is individually driven, okay. That is the one thing. In the conventional machine, what you have seen is the prime drive, one drive, and that drive is making the or transmitting the power to the output shaft, okay, and the feed is taken from there only. So, there is only one drive for the entire machine. Here what happens in these machines, so this power is given to the x, y and z individually, so that individually these axes can be driven, okay, x, y, z axis can be driven. Therefore, what happens that any kind of a configuration that you want with the help of a combination of the movement of along the x, y and z axis, you can actually achieve. So, as a result, what happens is that in comparison to conventional machine, where you can for a particular machine, on a particular machine you can actually machine a particular part. Let us say an example is the turning lathe. So, there we call as a turning lathe, because only the turning process can be made. So, certain parts can be made only. For example, you cannot make parts that can be made on the milling machine, not all the parts, like flat surfaces, okay, like in case of bigger flat surfaces you cannot make in the turning, all right. Grooving you cannot make. So, you cannot make, for example, a contour surface, okay, in case of turning in the turning. So, this is the difference between the conventional machines and the NC numerically controlled or the CNC machines. CNC stands for computer numerically controlled, NC stands for the numerically controlled machines. In the case of the CNC and the NC machines, since all the axes are individually driven, you can have any kind of a relative movement between the tool and the workpiece, and as a result various configuration of the parts can be made here. You can make a shaft, for example. Using the same machine, you can make a gear, you can make a flat surface, and so on. So, those are more flexible. To increase the flexibility of the machines, of the conventional machines, these kind of machines are introduced, and as I told you, it is roughly about 1952-54 when these machines have been evolved. All right. Now, what we are going to show in these machines is that first we will go for the turning, and if you see that this is the drawing for the part. So, this I have already shown it to you through the PowerPoint presentation. So, we are going to make out of this the blank, we are going to make a part like this, where we have the flat surfaces, we have the tapered surfaces, we have the thread, we have the chamfer, we have the groove, and we have the semicircular or the radius of the particular side. All right. So, now in doing so, we will be showing you that what kind of movements the tool has to make. All right. For example, in this, to make this length, all right, to make this length 65, out of a length which is more than that, you have to face it. So, the tool from the 0 position, it will go to certain part, certain point, and then it will face it. So, it will remove the excess material from the blank as well as from this side. So, this is just an example of a very small movement of the tool. So, similarly, you will have the different kind of movements like to make the taper surface, to make the chamfer, to make the threads. Here if you can see that there is a thread made. So, all these operations we are going to show you in the turning CNC, and similarly in the for the turning for the CNC milling, we are going to show how a part like this can be made. All right. And the entire procedure I have already described to you, and here it will be shown to you that how this can be made in a machine. So, for milling it is little different, as you can see that there are semicircle, radius is given, here it is the radius given like that, here it is the inclined surface, these are the straight surfaces and so on, and how they can be programmed, and what kind of symbols are used for the programming, that will be shown to you, and that will be demonstrated to you how this can be implemented. Now, before we go to the machine, let me tell you that first the program is made having the drawing, any kind of a drawing of a part that you have to make. Having that, we have to first make the program manually. So, when the program is made manually, knowing the codes, knowing the symbols, as it has been told to you, there are different kind of codes from A to Z, all right, and each one symbolizes something. For example, there are G codes, there are N codes, there are M codes, and so on and so forth. There are A to Z, all the 26 alphabets are used for making the program, and each of them means something that I have already told to you. Similarly, there are digits from 0 to 9, okay. There are points, there are plus, minus signs, okay, and so on, and each of them indicates something. For example, if you have to change the feed, so you have to symbolize that feed as a F. If you have to change the speed, so you have to symbolize that with the help of a letter S, stands for the speed, and so on. So, overall each letter, each symbol make something to understand for the machine. Machine has to understand these this language or these codes. So, we will tell you how these codes can be made, can be generated, and how it can be interfaced with the machine, how it can be put it on the machine, and how the machine can execute that. Okay. So, but before that, before we go to the machine, we have to make sure that the program that we have made is flawless. So, you understand that there are various parts. The parts can be very complicated, and for those complicated parts the programming can be very complicated, and very a lot of lines in the program can come. Okay. So, each line has to be executed. Now, when you are making the program manually, okay, a flaw can come, somewhere point is missing, somewhere one sign is missing, somewhere some digits are missing. So, this has to be simulated, this has to be made sure that the programming is right. So, there is a simulation software, we will show it to you that how it can be simulated. In the simulator, this program that you have made manually, this has to be input, and then each line has to be executed to see how this line, according to this line, the machine is, how this line is understood by the machine, and how this machine is executing this line and the program. And finally, you can see that there will be a relative movement between the tool and the workpiece according to the program that we have made, and the entire part is being machined. So, that is one side of it when you are making the program manually and then putting the program in the machine. So, as I said, the programming can be made manually, that is one part of it, but then that program, how you are putting that in the machine. So, in here there is a display. If you see this machine, this is the Nemco Concept Mill 250, this is the machine. Here also you have a keyboard, all right, and there is a display. So, the program that you have made on a piece of paper manually, for example, beforehand, depending on the part that you have, this program can be input to the machine through the keyboard that the machine has. There is an inbuilt keyboard, all right. So, using this inbuilt keyboard, and each time you are pressing a key, it will be demonstrated here. You can see in the display that will be shown to you, and this way the programming can also be made and put it in the machine. So, then when your program is made here, okay, input here is given here. After that, when you are switching on, according to the program, there will be relative movement between the tool and the workpiece. But before doing that, make sure that the program is right, and you run it in the simulator, and the simulator is showing no conflict in the program is okay, and then only you bring that program, put it here and make it. So, that is only one part of it. Another way, this recently what has been done is that computer aided manufacturing is being used for making the program. So, in that there are special software used for that. We have a software which is Fusion, and we will show it to you how that Fusion can be used to generate the code, generate the program that you have made actually. So, as you understand that for that, first of all you have to have the part drawing. So, that part drawing you have to make in the Fusion, okay, using that Fusion software. So, you are making that part and giving all the dimensions which will be required in that, like for example, I have shown it to you here. Okay. Here this part is made and with all the dimensions. So, according to these dimensions your program has to be made. So, here we have made it manually as I narrated, but then using the computer aided manufacturing, the same program can be generated by the software, by the Fusion software. So, you have to actually make this drawing in the Fusion. Drawing according to that, the program software will understand that what are the dimensions and how the tool should move. Then the software is capable of finding out the optimum way how the tool should be moved, so that the entire part can be fabricated. After the drawing is made, of course, from that drawing you can make the 3D picture, 3D drawing, okay, and from there from the coordinates, from the dimensions, the program will be made, the code will be generated, and the same code that you have generated manually, it will be generated by the Fusion software, and that code can be then electronically transmitted to the machine. In that case, you do not have to really touch the keyboard to make the program and input the program in the machine. That will be then electronically transmitted, and according to that program which has been made by the Fusion software, the part will be made. So, in that case, of course, your simulation is not required, because the software itself making sure that the entire program which it is being made by the software is right. Thank you for your attention.